Welcome back, everybody. So let's continue. First, two things. First, I didn't notice the slides were not visible. So now if you go to the Moodle page, you should find the link in the last week, so 22nd of March, you will find the link to the slides, section 5 over there. I also updated the YouTube recording so that they're also linked from there, even though in general, you can always directly go to YouTube as well and find them. For today, I added, just in case we start part 6 on index compression, but that I don't know if we'll start today or not. So if we don't, I just shift it over to next week. Can you see it, everybody, on the Moodle? Just a confirmation? Can you see it? Awesome, perfect. So that's the first thing. The second thing is that I saw in the Zoom chats, there is a question which was also asked during the break, but I also do it live. Maybe you can read it.
What if there are too many pairs with the same key to all fit on one machine?
Mm-hmm. So that's basically the question that you, it was you, right? That you asked during the break. So there is indeed an assumption in MapReduce that when you shuffle, the number of pairs corresponding to the same key must fit on the same machine. That's kind of a requirement. Otherwise, MapReduce doesn't work. At least the architecture of MapReduce wouldn't work anymore. Now, this optimization that one of you mentioned in the first hour, called the combine function, is one way to address that. Because if you want it to fit on a machine, you can maybe compress it by merging. For example, imagine you're counting Pokemons. If you have a pair with 2 Pikachus and a pair with 3 Pikachus, then you can just combine it to a pair with 5 Pikachus, right? And then you reduce the number of key values, but without affecting the correctness of the results. So this is called combining, and that is one way of reducing the number of keys and making it fit. And the other idea, and this is actually a clever idea that you mentioned, which is the idea of changing the architecture of MapReduce in order to support some enhanced way of merging the key values if they don't fit on a single machine, a bit like SPIMI. But what I answered is basically that it's always a matter of how much does it cost and what benefits do you get. Basically, the MapReduce architecture, what makes it so powerful is that it's simple and it's the same for all use cases. There's only one. So the cost of changing your strategy, because if the keys do not fit, then you just need to revisit your strategy and find maybe a better way of implementing your map and your reduce function. The cost of that might be much smaller than completely redesigning the architecture of MapReduce. Because if you want to do that, completely change MapReduce, it's probably going to cost you millions of dollars, all the cost of people working over that for 1 year, solving the problem and so on. Now, the question to ask yourself, if you put $1 million in that, probably you'll need investors and so on. Did you do it in a way that is generic to any problem? In what case, maybe it's worth it, right? You can turn it into an open source project and other people can use it. Or did you just put $1 million into something that is only specific to a single use case? In which case, maybe that's too expensive, right? So it's always the question to ask yourself, do you really want to change the architecture of a system? Or is it not less expensive to just adapt yourself to the existing system instead? Which is also a way of seeing that. Did it answer your question? Waiting for a reaction on Zoom. We assume that's... Okay, so we'll assume that it answers. Otherwise, just let us know. But again, the idea is that whenever you design a system, there are assumptions, right? And MapReduce indeed makes the assumption that all the key values with the same key must fit on the same machine, right? Otherwise, it breaks. Was it a yes? Awesome, perfect. Okay, so that was the reduce where you built your standard inverted index. And when you get all of your key values where the key is a term and the value is a posting list, what do you get? You get the standard inverted index, right? Written back to disk. In fact, what we've seen is exactly what the architecture of a web search engine looks like. We can implement that with MapReduce, literally. Where we parse the documents, in fact, what we have here is the URLs that are known to us. And then what happens is that the mappers will download the web pages, generate this, and then massively on a data center, download and index the entire internet. That's like magic, right? So today, maybe it has changed, but at least 10 or 20 years ago, this is how it was done. Now, probably it was optimized even more, but this we've just built a Google, basically. I can put it like that way. Okay. Now, in the architecture that we study in the big data course looks like this. We basically have a node that's called the job tracker, and then we have the nodes called the task trackers that contain the data and that build that map and reduce. I should remove the toolbar because it's the trick that predecessor of you told me in another class. I need to click here and then to close the window, and then that magically disappears. Yeah, like this. Yeah. Okay. But that, again, this is big data material. So that's just to give you an impression. And we actually have a cluster with thousands of machines in order to do that. And the idea is that we have a whole distributed file system that we also teach in big data that is organized in blocks. That's called HDFS, the Hadoop distributed file system. And we basically read the blocks from this. So the blocks, these are the shards that I told you about. And then we process them one block at a time. Every time you get the one mapping machine that takes care of it. All right, but again, come back to the big data course. We'll do that in details. What I wanted to show you is how you can build an actual search engine using this technique, even if the data doesn't fit on a single computer, right? So again, first exercise in the semester, this is when the data fits in memory. BSBI and SPIMI, which is a better version, is when the data fits on your disk, but not in the memory. And MapReduce is when the data doesn't even fit on a single machine. Okay, so far so good? Okay, so now let me switch to the next topic. Imagine you've just downloaded the entire internet and indexed your engine. The thing is, the web has a life. The pages change, they get updated and so on. So after an hour, your index is already no longer up to date. So what do you do about it? Right? How do you deal with the cases that new documents get added, documents get updated, and so on and so on, right? Now your index is basically no longer up to date. So what you could do, this is one way of doing that, is that you just rebuild the entire index, right? Typically, maybe it has changed, but back then, the delay was technically 2 days, right? So every 2 days, you would get a fresh index. So it's a bit of a naive technique, but it works. You just periodically rebuild the entire index, and you just need to accept that there is a bit of a delay and it's not completely up to date. Any changes of less than 2 days might not be reflected in the index, right? Every 2 days, you reconstruct the entire thing. That's the first approach. But again, staleness, this is this idea that it's not up to date. And you might also, while you are reconstructing the index, of course, you're probably going to keep the first index while building the second one, but it slows down the entire systems, right? Except if you have completely different machines. Have you heard of double buffering in computer graphics? It's a little bit like that you could do. Like some machines have an index, the other one being constructed, and then you swap the two parts. Okay. But there's a second way to deal with that. By the way, the name of that is online index construction. Online index construction is how you deal with a collection that keeps changing over time, right? It's also the case for a library, for example. Once you have indexed an entire library, there will still be new books that get added and so on. Solution number 2 is to have a second index that contains the most recent changes. Solution number 2. So it means that we have the main standard inverted index that took us 2 days to build is here on the machines in your cluster. And when new documents get added, we just do them on the fly in some auxiliary index, could even be in memory. And that is much smaller, and we just maintain it, right? So this is one way of doing it, that we just keep that extra index. What that means is that when somebody outputs a query like computer, then you need to look at 2 places. You need to check this main index, the long-term index, plus you need to check if there's not something newer that might be in the auxiliary index, right? You always query both. So this is one way of doing it. And what happens is that you let the auxiliary index update itself, but at some point it's going to start growing, right? The auxiliary index is going to grow. And then at some point you merge it back into the auxiliary index, right? Periodically, maybe, I don't know, every 2 days, every 3 days, you just merge back and so on. But everything that's new basically gets into the auxiliary index. And by the way, if you just add new documents, it's only appending, right? You're only appending to a file. And in big data, we love appending to a file. That's something that is very easy to do. Okay. All right, and it's very efficient because imagine that every one of these postings this here is a single file on disk. It means that you have a seek, a latency every time you update one of the terms, but even if there are several documents to add, it's a single seek, right? But there's still a problem because that addresses the case where new documents get added, right? New documents get created, then we use the auxiliary index. What about a document that gets deleted? Because if you see what's going on here, if we delete a document, it means that we want to remove something that is on the disk, right? And that is very expensive. We cannot do that. We cannot remove a posting list in the middle of that. That would be a random access right? We want to remove a specific item there. So we cannot do it. We cannot just remove it from the index. But what we can do is something actually that is a very popular technique at very large scales, is that instead of deleting the document, you mark it as deleted. You keep it, but you mark it as deleted. So it means that we can have an extra structure that is also called a bitmap, just like these very old pictures. It's a bitmap with 1 bit per document ID, right? You have all the document IDs that give you the position in that bitmap. And when you delete one of the documents, you just mark it as deleted. Maybe I should add an extra mark in there to distinguish the red and the green. But basically, you do a mark right there, and that basically tells you that document ID here is deleted. And then it means that when you query over there, you need to filter. If it's marked as deleted, you filter it out, and you only forward those that don't have the document marked as deleted, right? So this is how you can deal with document deletion, right? Of course, you need to consider, because that's the technological aspect, then there is the law and the data protection aspect, right? From a data protection aspect, this is not enough. If you want to implement a user who asks you to delete information, it's not enough to put an invalidation flag. You really need to make sure you delete it from the system, okay? But again, the next time you merge the auxiliary index, you can also, in a single pass, as you copy over to a new version of the index, you can just use that opportunity to remove the invalidated documents, okay? So this is the first improvement. Here's another improvement. Imagine that we have now, we index the entire internet. Imagine that we have millions of terms, millions of postings lists. Then we cannot afford to have latency for every single one of these terms. That doesn't work. So we need to maybe group them into less files, right? That's because of scalability. So basically, there is some sort of slider here in the design that we have that we can find something in between having one file on the disk for every single term, that's a lot of files, or a single file with everything, that would be too big, right? And somehow in the middle is the sweet spot, right? You basically group some of the terms together in files, and then you have several files like this. And this is kind of, you need to experiment and play around and find out what works, right? It's about the granularity. Again, we consider that for big data, the ideal size and so on. We'll cover all of that in the master's lecture. So now, if we try to think a little bit in terms of complexity analysis, just on a high level, we have these incoming postings, these incoming tokens, that come from the documents. The letter T in that respect is the number of tokens. Remember that N, big N, is the number of documents. Big M is the number of unique terms in your index. T is typically used for the number of non-positional, for the positional tokens, the ones that come from the original documents, right? So T. Now, we periodically merge the auxiliary index into the big index. So it means that if we call n, small n, here it doesn't mean, it's not a standard notation, but if we call n the size when we decide to merge the auxiliary index, as soon as it has n tokens, we merge it, then it means that the number of times we merge is going to be T over n, right? N is the size of when we merge. T over n is the number of times we are going to merge. So it means that every time we merge, we are going to feed n new postings into the existing index. And at the end, at merge number T over n, if you do the multiplication, n postings multiplied by T over n, then you get T. That's the total number of tokens. For whom is that clear? Right? Just the division. So now, what is the complexity? Well, you remember that this is the second part of the merge sort. So the complexity is, anybody? On Zoom, maybe you're maybe, okay, if you all say it at the same time, what is the complexity of the second part of the merge sort? Linear, yes, you see, you know it. Okay, so this is indeed linear. So it means that merging with n posting is going to be n. Yes, on Zoom also, perfect. So you're with me. So the second part, so it's going to be 2n, 3n, and so on. So every time the complexity is whatever number of tokens we have so far. So we have in total n plus 2n plus 3n all the way to t. What is the sum of the first n integers? 1 plus 2 all the way to plus n, it's? Okay, say it all at the same time. What is the sum of the first n integers? I heard it, n plus 1 over 2, right? So that's exactly the idea. So n plus, I need to remove the toolbar. There you go. So 1 plus 2 plus all the way to t over n, and then we just factor out the small n. So basically, it's going to be t over n plus 1 divided by 2. So it's basically t squared over n squared, if you approximate it asymptotically. T squared over n squared multiplied by n, so that's t squared over n, right? I just got rid of when I say n plus 1 over 2, n plus 1 is the same as n asymptotically. So it's like n squared, typically in complexity. And n in that case, when I say all the integers from 1 to n, here it's all the integers from 1 to t over n. So it's the t over n that I need to square. So t over n squared times n gives you t squared over n. So that's the complexity we get. It's basically quadratic in the number of tokens, and then n is kind of a constant because that's just the size. It's a parameter, basically. Okay, the problem is we don't like quadratic. Quadratic in big data is not good. In fact, this is also why we don't like shuffling, because shuffling is quadratic. So it would be nice if we could get something that is better than quadratic. In fact, what we consider acceptable would be, for example, t log n, t log t. T log t would kind of be acceptable, right? But t squared, no, that's just too much. We don't like that. So is there a way of finding a different strategy than just merging every time the auxiliary index is full in such a way that we get a better complexity? And of course, the answer is yes, and I'm going to show you how. And this is actually a beautiful design that is also used again in big data, but in the context of white column stores. So that's one thing that you'll have to learn less in big data since you already saw it here. And this is called logarithmic merging. So it means that instead of merging the auxiliary index into the main index every time it's full, I'm going to completely revisit that strategy and do it in another way. Smart way. So here you go. on the top of the screen, that's what's in my memory. It's the auxiliary index, basically. And then at the bottom of the screen, this is what there is on the disk. So imagine that we start afresh. The internet is completely empty. It's 1989, and we start indexing it. And here come the first n documents. So we have our first standard inverted index of the very early internet that is in there, Z0, we are going to call it. It fits in memory. Now, after a while, we reach that size, n, so it's full. So what do? We send it over to the disk. That's there. We call it I0. Then the internet continues to evolve as more people join. The web, I should be more precise, the web, because the internet already existed. So the web. There's again n new web pages, n new postings in there in the memory. Now it's full. So we have the older ones that are on disk and the newer ones that are in the memory. So what do? I merge my auxiliary index with the entire index and put it back to disk. Now, I have a new single standard inverted index, but this one is twice as large as the first one, right? Now, I have, again, the web evolves and more people join and add web pages. So now we have n new postings. So we have this old index on the disk plus the more recent postings that are in the memory. So if we use the method I told you earlier, we would just merge these n postings into the index, and then we get 3 times the initial size, right? But we are not going to do that. We are not going to do that. Instead, we are going to write it down separately. We don't merge anything. We just write it to disk. So now we have 2 indices on disk. We have an index of size n, I0, and an index of size 2n, I1. We have 2 indices. That's the novelty here, 2 indices. If somebody wants to query, we'll just look at the 2 indices, right? And we'll just union the results from the 2 indices. All right? Then the web evolves. There's again new people creating web pages, and there's again new postings and so on. So now we have an auxiliary index. So again, if people query at that point, we need to look at 3 places for the query. We need to look at I1, we need to look at I0, and we need to look at Z0. Who is with me so far? Okay. Now, what do we do when it's full? We are going to merge it because there's already one of that size. So we merge it into a new index Z1. But now that we want to write back to disk, there's already one of that size. So again, we are going to merge. Now we have an index 4 times the initial size, right? 4n postings, and I write it back to disk. Now it means that on disk, I have a single index. Sorry, not yet. Press once too much. Yeah, I have a single index, I2, that is 4 times the size. And now I'm back to a single index. Now new people create web pages, there's new postings and so on. It's full, so what do? I write it to disk, right? Then again, new people create web pages and so on. I would like to write it to disk, but the slot is already taken, so I have to merge it. Here it's not taken, so I write it to disk. Now I have 2 indices, I1 and I2. So I have 6n postings in total. 2n are in I1 and 4n are in I2. Now a new index comes, I write it to disk and so on. Then a new one comes, and here you see what happens now. There will be a cascade, right? We merge, we merge, we merge. Now I have 8n, right? You see how it continues? What did we do? In fact, we counted in base 2. Let me show you. Let me rewind. You know how to count in base 2, right? You're a computer scientist. But just take the mirror of the number, because normally you write a number with the unit on the right and then the higher bits on the left. Here it's just mirrored. So this is basically you need to write to read right to left. This is 0, 0, 0, 0. So let me just tweet on top of that. 0, 0, 0, 0, 0. Now we have 0, 0, 0, 0, 0, 1. This is 1 in base 2. Now we have 1, 0. Now we have 1, 1. Now we have 1, 0, 0. Now we have 1, 0, 1. Now we have 1, 1, 0. Now we have 1, 1, 1. And then the cascade basically means now we have 1000. For whom is that okay? Right? We just count in base 2. And when we do that with this different strategy on how we write to this and how we merge, a miracle happens, because now if you compute the complexity, you have n postings, 2 n postings, and so on. So the number of indices will be the log of t over n. And the construction time now takes t log t. If you get rid of the n, which is just a parameter, it's t log t. This is much better than quadratic. So this is this design here that you just saw, the logarithmic merging. It's also called the log structured merge tree, LSM. It's extremely popular and has many applications also in the database world. This is a very generic idea that optimizes the construction time. Who here has already played the 2048 game? Many of you, right? I also played it. I love it. This is the 2048 game, in fact. That's exactly what's going on here. Okay, okay. So this is the construction time, T log T, and the query time is logarithmic because the number of indices is actually logarithmic, right? This is very efficient. Now, it's always a compromise, right? You want to strike a compromise between the time it takes to construct the index, the time it takes to query the index. Having said that, so the logarithmic merging has many applications in practice. We'll see in the big data course that it's applied to wide column stores, HBase, big table, and so on. But in practice, at least the last time I checked, you might find it boring, but in fact, people just reconstruct the index. So they really build an index, then build a new one in the background, and when it's full, they swap to it, then build again a new one in the background. So this is something that, that is more practicable at the scale of the web. So this is why you have this, whenever you add a website to the search engine, it might take a while until it gets added. Okay? So what did we do? We took the standard inverted index and we solved two problems. First, how does it scale if it doesn't fit in memory or if it doesn't fit to disk? Second, how do we deal with the case that the collection changes over time? It's an online thing. So now we've solved that. However, we have only solved it for the standard inverted index. But what did we do in the other weeks of this course? We extended the standard inverted index. We had the byword index, we had the positional index, we had many, many other indices. So can we generalize this to the other extensions of the standard inverted index? The answer is yes. Yes, absolutely. You can use the same thing if you want to build a positional index, a byword index, a keyword index. It all works. You can absolutely use these techniques. The same goes for the permuterm index and so on and so on. Exactly the same ideas can be used for that. For whom is that intuitive, that you can use the same techniques? Okay. Otherwise, you can think a little bit about it, but that actually works. Okay. So now, if we wrap up what we have done so far, we have this standard inverted index. The problem we are solving here is the problem of Boolean queries, right? Boolean queries, also maybe phrase search if you want, if you consider positional indices. What we have not done so far, we didn't even think about that or even touch that, is the ranked queries. Because if you want a true Google, you also need 10 pages on every page. You need the first 10, the top 10. That we have absolutely not discussed, how we find the best pages that you could output, right? So this is a problem that we still need to solve. Something else we didn't consider is the access control list, right? If we index the web, it doesn't matter, it's all public. But imagine you are a law firm, right? One of the use cases of information retrieval is for law firms. In that case, you might have internal data and you want to make sure that only people who are authorized can access them, right? So this is the conclusion of this lecture on index construction. It corresponds exactly to that chapter of the book, chapter 4. So I encourage you to read it. Who is reading, by the way, the book every week? Very good. You have to. You really, really should read the book because that I give you a perspective. The authors of the book give you a second perspective. It's very good to have several perspectives. Okay. Are there any questions so far? Index construction. On Zoom, any questions? No questions? You're sure you don't have questions? Okay. So it means, since we have a bit of time, we have no, all good things. Okay, that's not a question, but thank you for confirming. Awesome. So I will start with the index compression then. So the slides are already in the Moodle. If you go to the Moodle page of this week, you will find the slides. And I'll get started. So just give me 1 minute to stop the recording, do the switch and so on.